Hi, my name is Curtis Bechtel. I'll be talking about delegated stochastic probing, which is joint work with Shaddin and Dughmi. To motivate our problem, I want to talk about transportation. We can imagine for some city that the city mayor wants to design a new public transportation network. They might delegate this problem to an expert contractor who knows more about how to design such a network than they do. But the contractor probably has other interests involved. They may prefer designs that put bus stops at their own headquarters, or designs that improve the roads in their own neighborhood, regardless of whether these are good for the city or not. So the mayor asks us how to incentivize the contractor to produce a design that's good for the city, rather than just good for the contractor. We could call this problem delegated search, and it's a principal-agent type problem in which the agent searches for solutions to the principal's problem, and the principal cannot search for their own solutions for whatever reason. We take inspiration from the work of Kleinberg and Kleinberg, and delegated search approximates efficient search. In their paper, they describe a distributional model in which the agent can sample k independent solutions from a single distribution, and then they must propose one of those samples to the principal. They also describe a binary model in which there are many different potential solutions, and each one has a fixed utility for both agents, but randomized feasibility, and checking the feasibility of an element incurs costs to both the principal and the agent. And they show that for both models, the principal can design a mechanism which gives them a 1/2 approximation for a very particular sense of approximation that we'll describe later. As an overview of our results, we start by modeling delegation as a game-theoretic version of stochastic probing problems, defined broadly. We then show that simple mechanisms are just as good as general mechanisms, and this is much like the revelation principle. We show that delegated stochastic probing can be reduced to a combination of profit inequalities and adaptivity gaps of a particular character, and then using this, along with known results, we get the following two corollaries. First, we show that we have constant factor approximations for a very large class of these delegation problems. Secondly, we show that there's a 1/2 approximation for a generalization of the distributional model of Kleinberg and Kleinberg. This is a generalization in which we allow heterogeneous distributions. Finally, we show that randomized mechanisms sometimes outperform deterministic ones, but not in general. And this provides evidence that maybe randomized mechanisms perform just as well and no better than deterministic ones in the worst case. We'll start by defining a non-game theoretic problem called stochastic probing. Broadly, this is composed of a set of elements E, where each element has a random value x sub E. There's an outer constraint limiting the set of elements we can probe, and there's an inner constraint limiting the sets of elements we can accept. The procedure in this problem is to probe elements subject to the outer constraint, so the elements we probe have to be feasible in the outer constraint, and accept a subset of probed elements. This time, the set of elements we accept has to be subject to the inner constraint. Our goal is to maximize the sum of the values of the elements we accept, and this is in expectation, of course. As an example, we can consider the following graph. This is a stochastic probing problem in which elements are the nodes of the graph. Our outer constraint, our probing constraint, is a 4-uniform matroid, so we can probe at most 4 elements. And our inner constraint is the independent sets of the graph, so we can accept any independent set. I haven't described the distributions of the elements. We can assume that they're known if we were really trying to solve this problem. But for our purposes, we'll just ignore that. So we might imagine we start by probing element A to reveal a value of 5, and then element E to reveal a value of 8, and then D, and then F, in that order. Now, once we've seen all of these values, now we have to choose an independent set to accept, and the best choice here are the elements A, D, and F. Now, it turns out that Kleinberg and Kleinberg delegated essentially the following stochastic probing problem. We can imagine a problem in which there are k identically distributed elements. There's no outer constraint at all. We're allowed to probe all elements. And there's a one uniform matroid inner constraint. And this is just the stochastic probing problem corresponding to their distributional model. We can also imagine other types of stochastic probing problems that we might want to delegate. For example, a transportation problem could be defined as follows. We have some number of bus network designs and some other number of subway network designs. We have a total fixed amount of time available to us, and each design costs a certain amount of time to evaluate. So we want to evaluate as many as we can, but we need to be strategic about it. And ultimately, we want at most one bus network and at most one subway network. And in general, we may want to delegate arbitrary stochastic probing problems. So this leads us to define our model as a delegated version of stochastic probing as we defined it earlier. This consists of a ground set of elements E, where each element has a known distribution over utilities x for the principal and y for the agent. We allow x and y to be arbitrarily correlated, but each distribution from different elements must be independent of each other. We also have an outer constraint on the set of elements that can be probed. This is the probing constraint. And again, an inner constraint on the set of elements that can be accepted as a solution by the principal. This is the accepting constraint. Our goal is to design a mechanism maximizing the principal's total utility for accepted elements in expectation. We take the perspective of the principal here. Just as some brief notation before we get started, we call an element along with its utilities, so the triple E, x sub e, and y sub e, we call that an outcome. We call set S of outcomes whose elements are feasible in the inner constraint a solution. So anything that the principal could accept is a solution. Omega here is the set of all solutions. And we also write little x and little y as utility functions. So for a set F of elements, x of F is just the utility that we expect to get, the utility that we get from those elements. And for a set S of outcomes, x of S is the utility from those outcomes. To solve this problem, we propose the following mechanism. It starts with the principal committing to a family R of acceptable solutions. And this means that if the agent proposes a solution inside R, the principal commits to accepting it. And if the agent proposes one outside of R, the principal commits to rejecting it. The agent, in response, probes elements adaptively subject to the outer constraint. And once they're done probing, or while they're probing, they receive the set of outcomes S. The agent then proposes a solution T, which is a subset of S. And if that solution T is acceptable to the principal, then the principal accepts it, and both principal and agent get their respective utilities for that solution. Otherwise, they both get 0. The principal rejects their solution, and we call this the status quo. Nothing changes. As an example of this in practice, we can consider the same graph from before, where the elements are nodes. The outer constraint is a 4 uniform matroid, so again we probe at most 4 elements, and the inner constraint are the independent sets of the graph, so we can accept any independent set. And a reasonable strategy for the principal, you might guess, is to set some kind of threshold. So the principal says they'll accept any solution S where their utility for S is at least 10. The agent, in response, probes elements A, then E, D, and C, for example, receiving the following utility pairs. Now, CD is the principal's favorite solution from the available solutions, and AE, a totally different solution, is the agent's favorite. But notice that AE is not acceptable to the principal, because the principal's utility is only 7. Therefore, the agent will try to propose their favorite from among the principal's acceptable solutions. In this case, AD is the agent's favorite acceptable solution. And it's really a compromise between the two. The principal didn't get their favorite, and the agent also didn't get their favorite. So therefore, the agent will propose that solution, and the principal will accept, because they committed to accepting it. So we call this mechanism a single proposal mechanism, and it turns out to be actually very powerful. Here we'll generalize the result of Kleinberg and Kleinberg, which says that single proposal mechanisms are actually just as powerful as a much broader class of signaling mechanisms. And we're transforming their result into one that applies for our model. We can define signaling mechanisms as one for which the agent can send any signal they want, and the principal will then transform this signal into a solution by a transformation function that the principal chose. And we get the following lemma that says that for any signaling mechanism for our delegation problem, there exists an equivalent single proposal mechanism. So we can consider, without loss of generality, single proposal mechanisms from here on out. Now, for our purposes, we're interested in approximately optimal mechanisms, and we define approximately as this delegation gap. Delegation gap is a comparison of the principal's delegated utility, which is the utility they get when they're delegating, and their non-delegated utility, which is the principal's expected utility when they search on their own using the same constraints as the agent. This is the same as their utility when they solve the stochastic probing problem associated with the delegation problem. And so the delegation gap is just the ratio, it's the worst case ratio between these two quantities, the optimal delegated utility and the optimal non-delegated utility. And this answers the question, how much does the principal still get when they delegate to that agent? As a detour before we get to our first result, we need to talk about profit inequalities. In particular, the generalized profit inequality problem consists of a set of elements E, where each element has a non-negative random utility, x sub E. We have another constraint system, M, and the procedure for this problem is for an adversary to order elements in advance. Then the gambler learns the realization of each element in the order set by the adversary. The gambler, upon seeing each element, must irrevocably accept or reject that element, such that the set of elements they accept is feasible in the constraint. This must be done in an online fashion. The gambler aims to maximize the sum of the elements they accept, and we also have a prophet who plays the same game as the gambler, but they know all realizations in advance, so they always get the maximum possible utility. Then an alpha factor profit inequality for this problem says that the gambler has a strategy with expected utility at least alpha of the prophet's expected utility. We're interested in two particularly strong variants of the generalized profit inequality. First, our adversary is called the almighty adversary. It's much more powerful than the standard adversary, and this one knows the gambler's strategy, random variables, and the realizations of all elements in advance. Therefore, the adversary can simulate the gambler's strategy perfectly and choose a truly worst-case ordering for the gambler. We're also interested in greedy strategies for the gambler. We restrict the types of strategies that the gambler can use. In this case, a greedy strategy is defined by a downward closed family we call A of solutions, or subsets of elements and their realizations. The gambler, employing a greedy strategy, starts with an empty solution S, and at any time when they have solution S, and they see a new outcome, E with realization X sub E, they accept that outcome if and only if the outcome along with their current solution is still in A. Now we can use profit inequalities using greedy strategies against the almighty adversary to help solve delegation problems with no outer constraint. And here we'll use a reduction from delegation to these profit inequalities to do so. To see why this might be the case, we'll compare delegation with profit inequalities. And here the delegating principle is analogous to the gambler. The non-delegating principle is analogous to the profit. And the agent is analogous to the adversary. So the delegation problem starts with the delegating principle committing to a set R of acceptable solutions, and the profit inequality starts with the greedy gambler committing to a strategy A. Then, in response, the agent can probe all elements because there's no outer constraint, and they'll learn all realizations of the elements. For the profit inequality, the adversary always knows all the realizations. For delegation, the agent then chooses what realizations to show to the principal. And similarly, in the profit inequality, the adversary chooses the order of elements to show to the gambler. Finally, we have a non-delegating principle for delegation, which always gets the optimal solution, and this is what we compare our delegating principle to. And in the profit inequality, the profit always gets the optimal solution as well, and that's what we compare our greedy gambler to. Formalizing this intuition, the similarities between these two problems, we get the following theorem, which says that there's an approximation preserving reduction from our delegation problems without outer constraints to profit inequality problems with greedy strategies against the almighty adversary. Using this theorem, we get the following corollaries. First, we show that there are constant factor strategies for delegated stochastic probing problems that don't have an outer constraint, and their inner constraint is the intersection of a constant number of matroid, matching, and knapsack constraints. This follows from the work of Feldman, Svensson, and Zinklusen in contention resolution schemes. They show that there are greedy strategies, greedy profit inequalities, that give constant factor results against an almighty adversary. We also get the second corollary, which says that there's a 1/2 factor strategy for delegated stochastic probing problems, again with no outer constraint, and a 1 uniform matroid inner constraint. And this generalizes the result of Kleinberg and Kleinberg, this time to heterogeneous elements, heterogeneous distributions. And it follows from the very famous single choice threshold rule of Samuel Kahn. Now, as a detour before we get to our more general results for inner and outer constraint delegation, we need to talk about the adaptivity gap, which is defined for the problem of stochastic set function maximization. This is composed of a ground set of elements E, where each element in E has a random value x sub E, and these values are independent of each other. We again have a constraint system M, and we have a stochastic set function, which I'll call U, from subsets of elements to non-negative reals, such that U of a set of elements F is completely determined by the random values of those elements. Our procedure for this problem is simply to probe some set of elements F such that that set is feasible in the constraint. And our goal is to maximize the expected value of U of F. Now we can consider two different types of strategies for this problem. Adaptive strategies, which is the general case, can choose the next element to probe based on all of our knowledge from previous probes. On the other hand, we have much more restrictive non-adaptive strategies that have to choose the set of elements they're going to probe in advance. and then they commit to probing all of the ones that they chose. The adaptivity gap, beta, measures the worst case ratio of these two quantities, the optimal non-adaptive expected value to the optimal adaptive expected value. And this answers the question, what fraction of the optimal expected value can we get when we're only using a non-adaptive strategy? Now we can use the adaptivity gap along with our previous result to get delegation gaps for delegation problems with inner and outer constraints. The basic idea here is to define a function u to be the optimal utility that the non-delegating principal gets when they probe exactly the elements f. Then we can use the adaptivity gap for the function u on our outer constraint to find a set f feasible in the outer constraint that approximately maximizes u. Now, given this set f, we can consider the restricted delegation instance, restricted to only the elements in f, and then because f is feasible in the outer constraint is no longer relevant. It no longer restrains us. So now we can use this to run our previous mechanism, which works when our delegation problem has no outer constraint and only an inner constraint. And this is the basic idea. Formalizing this intuition, we get the following theorem, which says that there's a reduction from delegation problems that removes the outer constraint, losing only a factor of the adaptivity gap of weighted rank functions of the inner constraint on the outer constraint. So we lose only the factor of an adaptivity gap to remove the outer constraint. As a corollary of this result, along with our previous corollary, we get that there are constant factor strategies for delegation problems with any downward closed outer constraint and an inner constraint that's the intersection of a constant number of matroids. This follows from the work of Braddock, Singla, and Zuzik. Finally, we briefly investigate lottery mechanisms, which are a type of randomized mechanism. The procedure here is very similar to our deterministic mechanisms from before, with one slight change. The principal starts by committing to a menu of distributions over solutions, rather than before they commit to a menu over deterministic solutions. In response, the agent will still probe as usual, and then propose one distribution from the menu, rather than proposing a solution. The principal finally accepts a sample from that distribution that the agent proposed. We're interested in comparing how good lottery mechanisms are when compared to deterministic mechanisms, and we do so in the special case of no outer constraint and a one uniform matroid inner constraint. We show that there are some instances where lottery mechanisms have a delegation gap of 1, or essentially 1, whereas deterministic mechanisms have a gap of 1/2. So lottery mechanisms perform much better. But in some worst case instances, both mechanisms have a gap of 1/2, and this is tight. And this provides evidence that lottery mechanisms do not do better than deterministic ones in the worst case. I'll leave you with some open questions from our work. First off, are these factors tight? We give a bunch of constant factors, but we only know one that's tight. In particular, we know that 1/2 is tight for instances with no outer constraint and a one uniform matroid inner constraint. And this is true even when we're using lottery mechanisms. But for other instances, we don't know. We can ask how hard it is to compute these strategies. What computational complexity does it require to compute the strategies we described? What if each element has a probing cost instead of or in addition to the outer constraint? And this is inspired by the binary model of Kleinberg and Kleinberg. What if the principal can incentivize the agent with payments? If they pay for preferable solutions, can the principal do better than without paying? And what if the principal delegates to multiple agents simultaneously? Can they get those agents to compete with each other and get a better outcome for themselves? With that, I'll leave you there and thank you for listening.